Evening, everyone, and thanks for joining us. We are now in I guess, the second half of our third series of working group sessions that we started, I think, late in 2019, and since the pandemic went virtual, and I guess same time national and even global. But our goal here is really to, as the title of this particular series says, to break down barriers, in this case, to building science, but also to enabling and empowering, our firms, architecture firms, design firms, to achieving, decarbonized buildings and achieving the 2030 commitment towards carbon neutral buildings by the year 2030. So today's session is focused on simplifying sunlight, and this is just one of the many simplifying solar energy analysis, I should say, not simplifying sunlight. But this is just one of the tools that really should be in our arsenal towards achieving the 2030 commitment. And at the same time, if you want to go to the next slide, Santi, one of our goals here is to really break down barriers to getting more firms to sign on to the 2030 commitment. And in speaking to that, it's important to kind of understand the myths and the hesitations that people might have in signing on to the 2030 commitment, but actually focusing on the facts, and that the typical time it takes to report a project every year is less than 30 minutes, and I can speak to that from experience. The program is free, and personalized mentorship, including from our committee, is available, and all you have to do is reach out to our committee, and we'd be happy to help kind of point you in the right direction, and that's what we're here for. And again, and also another concern is, well, I'm not gonna make the 2030 commitment, and I might have some projects that aren't performing very well. All of that is only visible to your own firm internally, but it tells you where you stand, and in knowing where you stand, then you can start to make progress. And I think that's really one of the most important things, is that we're all bringing all of our projects up to, up closer to the 2030 commitment, and by improving your lowest performing projects, you may be doing just as much as improving your highest performing projects. And another kind of misconception is that this is something you do after the fact. And I think one of the most useful things that firms that have been reporting for a couple of years are finding is that this is a great way to set benchmarks early in the design phases, and understand what you're actually trying to achieve in terms of energy performance. So it's a really useful tool, being a part of the commitment and reporting through the DEX in and of itself. And now at this point too, the AI 2030 commitment is issuing badges when you report, such as the one you see up on the screen, and it's kind of a nice achievement to be able to report to your firm, and to use them for marketing purposes. So what you do once you have signed on to the 2030 commitment, what does it entail? Well, first you sign a commitment letter, and then the next step is to create a sustainability action plan. And I'll talk about that a little bit more in a moment. And as we were talking about, you report all your projects through a database, a web-based database that AIA provides, which enables you to see all of your projects, your whole portfolio together, which is something that, for instance, going through the LEED certification process doesn't allow you to do, is kind of compare all of your projects. Then you pursue endeavoring to meet your targets. And then you kind of reassess as you get into this a couple of years, and look for ways to continue to improve your progress. But I can tell you from experience, is if you do join on to this commitment, you'll start to see improvements in your performance. If you want to go on to the next one. Thank you. So I mentioned one of the first steps is to set up a sustainability action plan. The AIA had just put out, actually, I think that's in March of this year, an updated guide on what it takes to create a sustainability action plan, some tips. There's also a number of examples out there. A lot of firms put their sustainability action plans out there on their websites. It's obviously an important part of many of these firms' mission statements. Going on to the next. Good. Okay. And so another thing I want to mention, and I think now, maybe if I'm not mistaken, we're transitioning to YouTube for our videos, but each of these sessions, those sessions that you saw from previous series, are being recorded, I guess, as of when we went to Zoom, so since March of last year. And they're a really useful resource, lots of different topics, all, again, geared towards meeting the 2030 commitment. So without taking up any more time, I wanted to turn it over to Janki, Ksenia, and Kajal to present tonight's topic, Sunlight Simplifying Solar Energy Analysis.
Thank you, Josh. So welcome, everyone. We are going to get started with our session today. And there you go. So this is part one of two sessions that we have that are related to the sun, I want to say. And in today's session, we're going to be focusing on just like basic fundamentals of solar geometry, and then looking at solar radiation analysis and how that can help you in your design projects to design better buildings and balancing solar radiation studies with energy and daylighting. And towards the end of the session, we'll go over many of the tools that are out there, and pros and cons of the different tools for solar radiation analysis and daylight availability. So with that, our two presenters today, we have Kajal Patil. Sorry, that's a typo error. It should be Patil, P-A-T-I-L, who is a recent graduate from the Master's of Science in Sustainable Design program at Thomas Jefferson University. And she's going to be going over the basics of sunlight and solar geometry. And we also have with us Ksenia, Knyazkina, who is a senior environmental designer and project manager at Atelier Ten in New York City. She's going to be sharing with us project examples that cover three perspectives on solar radiation studies. The first perspective is going to be massing and orientation. The second perspective is going to be facade and orientation. And then the third perspective is going to be photovoltaics and how you can use the solar radiation study to assess your site or building for the applicability of photovoltaic panels. So with the first perspective on massing, she's going to go over two projects, and then also two projects for facade and orientation. And for photovoltaics, she will review one project, kind of just laying the organization of the session. We are also going to stop at each perspective and Q&A. So if you have any questions that you have for Kajal or Ksenia, you can put them in the chat box, and when we pause for Q&A intermittently between the different sections, we can have a little informal conversation in between. Okay. And with that, I'm gonna pass the baton to Kajal, who will get started with fundamentals of sunlight.
Hello, am I audible?
We can hear you, yes.
Okay. You guys can see my full screen, right?
Yes.
Thank you, Janki, for the introduction. So before going to actual solar analysis part, let's understand sunlight fundamentals quickly. So the Earth travels around the Sun in a slightly flattened elliptical orbit. So what happens is the distance of the Earth from the Sun is closer in January than in July. The Earth's axis of rotation is tilted 23.5 degrees from the plane of its orbit. So the seasons that we experience annually are a consequence of this tilt. For this year, 2021, summer solstice is this weekend, that is June 20, which is the longest day of the year for those in the northern hemisphere, because the North Pole is tilted towards the sun. The vertical angle at which the sun rays strike the earth is called the altitude angle and is a function of the latitude, time of the year, and time of a day. There is this cosine law where the radiation received by a surface is a function of the cosine angle theta measured from the normal to the surface. So the vertical sunbeam which strikes the earth at 90 degrees experiences direct sunlight, which is much more warmth than the indirect sunlight. So as the altitude angle decreases, so does the heating of the land. So if we try to perceive the planetary motion from a location on the Earth's surface, imagine the sky as a huge hemispherical dome above our head, and the sun is moving on the surface of this dome. So if we see it in a plan, we see two curved lines which represent sun's path around a year, one on summer solstice and other is winter solstice. The longer the path, longer is the duration of the sun's stay in the sky. Throughout the year, the sun's paths keep shifting up and down between these two extremes. So we see the sun stays longer and higher in the sky in summers, while shorter and lower during winters. Coming to the solar radiation, it is a radiant energy emitted by the sun from a nuclear fusion reaction that creates electromagnetic energy. So this energy emitted by the sun is known as a solar spectrum and lies mainly in three regions: ultraviolet, visible, and infrared. Solar energy enters our atmosphere as shortwave radiation in the form of UV rays and visible light. The sun emits shortwave radiation because it is extremely hot and has a lot of energy to give off. Once the solar energy is in the Earth's surface, clouds and the other surface absorb that energy, and thus the ground heats up and re-emits energy as long-wave radiation in the form of infrared rays. As you all see in this picture, reflected radiation has longer wavelength and less energy than the direct radiation, which has shorter wavelength and higher energy. Diffuse sky radiation reaches the Earth's surface after having been scattered from the direct solar beam, which has also lesser energy compared to direct radiation. So as sunlight passes through the atmosphere, some of it is absorbed, scattered, and reflected by air molecules, water vapor, clouds, dust, and pollutants. So the amount of radiation that reaches ground is more when the sky is clear and less when it is cloudy. How to quantify radiation on the surface? The amount of solar radiation energy received on a given surface during the given time is measured in units of energy per area. So usually the direct estimates of solar energy are measured in watts per square meters in SI units or British thermal units per square foot per hour. So coming to takeaways, why do we need to spend time on solar radiation analysis? The first is to know where you have to heat the building versus where you do not. So where does solar passive solar work? Secondly, access where you need high performance versus low performance glazing products, which could help save money and materials in construction without increasing operating costs. Also, hello.
We can still hear you.
You can hear me, right?
Yes, you're clear.
Obtain early stage indications to understand seasonal outdoor comfort levels, that is making sure your outdoor spaces will be comfortable. The location of PV or solar hot water panels and best optimal angle for its placement. Impact of building massing, surface area and configuration and orientation on energy use or savings related to the solar heat gain or loss. So basically to understand how architecture and the sun relate or react to one another. So this is all with the fundamentals. Now I welcome Ksenia to present her study more in detail. Thank you.
Great. Thanks so much. Let me start sharing my screen as well. Okay. And now from fundamentals, we'll go to the specifics. So as Jeffy said, we're going to go through the three different sections: capacity implementation, facade optimization, and renewable energy. It's hard to talk about solar radiation and sun in general without touching the other topic. And we'll try to do so today because the daylight session is going to be next month. However, there will be a few times in today's session where I'm going to be explaining how we balanced our daylight and how we balance it kind of massing or facade optimization with daylight. So, you know, just a heads up, we're definitely going to talk about it more next month in way more. So to start this conversation, and to, you know, kind of walk you through how we look into the solar radiation throughout the whole design process, how we thinking about it, how we learn from it, understand some kind of guidance for our design and design decisions. I picked this project as I think a great precedent to look at and to understand that process. So it is in a governmental office in Boston, Massachusetts, so northeastern climate, close close to everybody, very, very relatable. It's the benefit to understand this radiation on this building case is that it has this big site, almost no context that would be shade in it, and the architects had the freedom to play around with massing, to play around with the geometry of the building, with the facade of the building, of its orientation on the site. So we actually went through quite a bit of studies and analysis to find that perfect design that would meet the sustainability goals. As a governmental building, it had pretty strict sustainability goals. The energy performance was a key. And even with very efficient MEP systems, it will be very hard to achieve that goal without high-performing facade and high-performing envelope, which in turn, hard to achieve. It's possible to achieve, but it will help if the mass and orientation were optimized for the site conditions. So additionally, they also wanted to have the daylight quality views for well-being and a great experience for the visitors in the building. So to start this process, so for us to give the recommendations to the architects, we first took a step back. This is basically what we do in all of the projects. Take a step back and understand what are those questions that we're trying to answer with this solar radiation analysis. What is that we try to optimize for? As a building in the north, well, actually, sorry, let's. So as we're asking these questions, we took a step back and looked at where this project is located, to look at the elements and the environmental conditions that we're working with. So in this case, we looked at the average hourly temperature for the whole year and daily incident solar radiation that we have on this site, on this climate. And basically what we're seeing is that, you know, no big surprise, the project is in Northeast. We have pretty cold winter and we have some hot hours in the summer. And if we combine this hourly temperature with the incident solar radiation graphs, we will see that our problematic sun or undesirable solar heat gain will likely happen from May to August, as the solar radiation is the highest and we have high outdoor temperature, while in winter and in mid-season, the solar radiation is kind of steadily goes down. In winter, the solar radiation is pretty low. So it's not going to be as much of a challenge. It's not going to be a problem, but it actually can help us to get some passive solar heat gains and maybe reduce the, you know, little bit of maybe our peak heating loads or some of our heating loads. While in summer, we will try to block this solar radiation to do a lot of things to reduce the total cooling demand, which in turn is going to lower our energy demand, improve the energy performance of the building, is going to reduce the utility costs, it's going to reduce the peak cooling loads. In terms, can reduce our size of the equipment that is necessary. It can, if we design the massing in kind of nothing applies, but with this information in our minds, we can also maybe reduce the amount of exterior shading that we need, which in terms, as Kajal said, we can save some money on that and some materials, so leading to a lower embodied carbon, etc., etc. All the great things, improve the environmental comfort, all of that. So from here, we're taking one step closer to the project and looking at the site. So for the site, I think this is kind of what we usually do. We're looking at the solar angles, you're looking at the altitude and the azimuth of the sun and a representative times, so the equinox, the solstices, and then looking at the context, how much of the shading the context is given us. We don't have to worry about sun on those sites. So this shadow diagram here is supposed to give us information. Our shadow diagram is a great tool to use throughout the whole, pretty much the whole your timeline project, from concept phase to the end of DD. You can be using that to work on the massing, to work on the shading, to understand how much of that sunlight and solar radiation exposure every representative point of the building is going to have. And then try to design your shading in there as well. So what our shadowing diagram is, it is a sun path right here, where this top line in here is represent for July 21st, and a bottom line in here represented December 21st. Each of this point, those kind of 8 look like 8 line, represents the hour of a day where the sun is located. And then those circles in here represents the altitude of the sun. So for example, if we'll take a look at June 21st at noon, our sun is going to be right here. And if we trace it for this circle, we will know that it's somewhere around 70 degrees, which we have confirmed with all our software. It's actually 71 degrees. So when we map the context, and this point have been is located on, I believe, 2nd floor in the middle of our site, we can see that the context doesn't do that much. We do have some shading in the afternoons, but it's happening kind of after 5 p.m. or right around 5 p.m. And it's in an office building. This is where people kind of starting to leave the building, so it doesn't really help us as much. And then we have almost nothing in the mornings. We have a little bit in here, winter mornings, but again, not much. And as the building is going higher, if we're going to be testing the points a little bit higher, we're actually going to have almost zero overshadowing from the context buildings. So we really have to work with the massing, with the facade optimization, with the shading to make sure that we are protected from the undesirable solar heat gains. So now that we know all that, now that we know that we want to, that we don't really have that much of a shading from a context building, we cannot rely on them, and that we need to shade our sun, to block the sun, at least from May to August, and try to use the solar heat gains and exposure to sunlight as a tool to reduce our heating loads in winter. We finally got to the solar radiation study. So this is a solar radiation for the summer period, from May to August, on the first massing that we got from architects. This is what they started with, and we were, our first step is try to understand how is it working, and then how we can optimize that. So as you see, going from facade to facade, our south facade, let's go here. Let's go to our legend, actually. Going from bottom to top, our north facade, which is not in here, which is going to be right there, the average solar radiation on the north facade is about 175 kilowatt hour per square meter. The unshaded north is, as a rule of thumb, is usually considered as a target solar radiation for all other facades. So looking where our south facade is in 225 kilowatt hour per square meter, we're quite close. We maybe need some window to a little bit lower window to wall ratio, maybe some spandrel, maybe some shading, definitely some shading, not just for solar radiation, but also for daylight. And then when we're looking at east and west, we are at 300 kilowatt hour per square meter, which is almost twice the north facade. So it is getting way more solar radiation that we want to see. And since the sun is low and it's kind of beaming almost directly to the sunlight, it's not just that, it's not just the radiation, it's also the daylight, it's also the glare. And this is something that we definitely want to resolve, because those are the times when you do not want to have that solar heat gain. For example, west facade, which is going to be right there, is going to be exposed to direct solar radiation, to the high direct solar radiation in the afternoons. This is an office building, so you have a lot of people, you have a lot of lighting, you have a lot of appliances. So all of that working during the day will produce internal heat gains. By the end of the day, your equipment is already working to cool the building down. And if we have all those internal heat gains and the solar radiation, kind of solar heat gains coming through that west facade in the afternoon, it's just going to increase those peak cooling demand so much, and it's something that we definitely want to avoid. South facade is, again, as I said, we want to resolve a little bit higher solar radiation, but since the sun is so high, it's usually something that is easier to manage because you need smaller shading, as we will see soon. And because it's also can provide us a good passive heating during the winter. Another thing to mention here is this big skylight that they wanted to introduce, skylight and kind of the glass wall all over east facade and on top. Now, atriums and skylights are a great tool to provide more daylight, and we all about daylight and providing the comfortable, healthy environment for our occupants. And that is something where we definitely want to balance the solar radiation. And because the skylight is flat and looking up directly up, especially during summer, it's gonna let a lot of solar heat gains through. So we would think that there's some exterior shading or some sort of shading device will be required. And as you see, it's way above than our max on the scale. So looking at all that, we wanted to go a little bit more granular and look at the hourly solar radiation analysis. I personally am a big fan of looking at the hourly data for your projects. It really helps, and maybe not specifically in this project because we don't have any context, but if you do, it really helps to understand what is happening there, how much of that, when exactly you have those problematic areas, how are they long-term or are they short-term? Because if they're long-term, you definitely want to solve that with some permanent measures, such as exterior shading. But if, let's say, you would have some high-rise building on the eastern here, and your building is only going to be exposed to direct sunlight for an hour or two, let's say an hour, that is something that is probably not worth investing in, the exterior shading, and maybe you can work with interior blinds or some other less expensive and less permanent measures. But in this case, we are all exposed from all four sides. But what it shows us is that on east and west, as we've seen on the pictures of the sun goes around the earth, as we've seen on all the sun domes and sun paths, on east and west, our solar radiation is the highest during those summer cooling period hours. It's kind of all going from April, from March even to October. And it's either in the morning on the east, in the afternoon on the west. But in the south, those cooling period is not as exposed, is not as critical, because in here we are getting some higher solar radiation, but the peak hours of solar radiation we're getting are in winter, when it's actually can be beneficial. So that's why we're really advertising this kind of the south-north orientation of the main facade while minimizing your east and west, to minimize that need for the dense shading on east and west, and use those big areas to collect as much as you can in winter. You can even work with the thermal massing, and the materials such as concrete and stone, or phase changing materials, which are very popular recently, really can, you know, collect and harvest that solar radiation, solar heat gains, and then release it when the temperature outside, or kind of later when you don't have those solar heat gains, release it into the space. So we really want to use the passive solar heat gains and this winter sun as a tool. So when we've been providing all this information to the architect as they're working in there, this actually was pre-concept phase, and they went through the whole process of, there was a lot of iterations of massing. We went through quite a bit of different types of either more compact buildings, because that's what can contribute to the high performance of the building, and then something which is more south and north oriented. All of those were assessed not just for their solar radiation, but also in our energy models and some very high level daylight analysis. In this case, we actually just did kind of the rule of thumb analysis, because we did not know what we're working with in terms of window to wall ratio, in terms of the layouts, etc. It's a pre-concept phase. So we used our rule of thumb, which is the height of the window head twice the height of the window head into the space. So just looking at all that, as well as I think considering some other project constraints and goals, budgetary, architectural vision, some recommendations from a client, our architect decided to go with the south-north orientation. To compare these two options, I would say that we can definitely work with both. It's nothing is not solvable, but this option have slightly less incidence of radiation during the summer, which is great, just because it has less east and west orientation, but it has way more potential for the winter solar heat, just because it has so much more south and north facades. As a result, as you will see in a few minutes, we actually could save quite a bit on our well, not sure how much was saved in terms of cost. I don't think we ever priced it, but a lot of material on our shading. And nope. So that was an example of the building that, you know, had all the freedom in a world of work with massing, with orientation, look at different options. However, it's not always the case. In a lot of projects, you are either constrained with the dense urban context, or with your site that, you know, you're working with a certain block and you have to fit in a certain maybe it's in a renovation. So for that, I want to talk about another case study, which was an existing building renovation. It's a renovation at New York Public Library building. So for that one, we started working on the schematic design. The building was supposed to be completely gutted from the everything on the inside, and all the windows and all the curtain walls of the storefronts on the bottom, on the ground floor, were replaced as well. So in here, our goal for optimizing the facade, our goal for running initial radiation to looking at the facade was to inform the glazing selection, to inform the interior layouts as well, because you need to know how comfortable it's going to be that perimeter area. Where do we want to place those workstations or lounge areas? It did inform the outdoor thermal comfort and this new rooftop canopy. So I'm not sure if you can see my cursor, but basically this building was existing, and then this big green roof on top is new. So the big goal for this project for the architect was to create a new program on the roof of the existing building. So they have this floor to ceiling glass extra floor as a conference room, the event space, covered with this, they call it wizard hat roof, which as you will see a little bit later, you'll have those big overhang, which helps with outdoor thermal comfort. So our first step was to do the overshadowing diagram, one of our favorite tools, and to look at the south and west facades and to see, are we really going to have that much of exposure to the sunlight? And is it going to be a problem? Is it something that is going to be long-term that we'll need to solve it with some permanent measures? As do we need high-performing low-E coating glazing? Do we need automated shading? Do we need, the exterior shading was not a question in here, but just understand what we're working with. And as you can expect in New York, in a very densely developed area, we did not have any permanent, any long-term exposure to direct sunlight longer than 2 or 1 hour. The south facade is barely open to direct sunlight. It's all diffused. And then the west facade was exposed just a little bit in, I believe it's 2 hours in summer in the afternoon, and then in winter again, just a little bit in here at 5 p.m. So our next step was to look at the solar radiation. And again, looking at our typical north and our unshaded typical north condition as our target is about 500, 570. If we look at our building solar radiation, the values that those solar radiation on all the facades are way lower than that. So that already gives us a clue that we're likely not going to have a problem with that, and we're likely not going to have problem with glare or overlit, and the daylight that is going to be coming from those windows is going to be this kind of quality diffused daylight, but likely not too much of it because it's still pretty overshaded. However, the roof is something that they really need to look into. So in here on the pictures to the right, you can see this kind of green wizard hat roof that they have, and then the floor to ceiling glass of this event space center. So seeing that this area is going to be exposed to direct sunlight, and to avoid, again, some high peak cooling loads, and also to avoid the outdoor thermal discomfort, because people are supposed to enjoy their time here outdoors with the great views and, you know, spending their day at the library. They provided this long overhang to shade both the facade and the outdoor area, outdoor seating area in here as well. So as you see, that you don't have to have all the freedom and big area, big site to use the solar radiation for your massing orientation. It can be useful to run that solar radiation, to look at the sun angles, to look at your hourly solar radiation on your facade representative points in the early design phase, so you can inform all those different decisions. I think this is where, yes, we stop with the massing. So I'm gonna stop for a second and see if we have any questions for this section.
So we don't have any questions in the chat box, but if anyone has any questions on the 2 projects that Ksenia showed so far, you know, feel free to unmute yourself and ask them now before we continue on to facade and orientation considerations.
Okay, great. We're also going to have time at the end, so all good. Great. So now that we've optimized massing, we optimized our geometry, we looked at the big picture. Now we can go a little bit more granular. So going back to our office building in Boston, this is what we got in our SD base. Again, it looks something a little bit more sketchy at the beginning, but basically this is the massing that the architects. And you see that they already started thinking about some shading, but they were looking for guidance from us. So we already have some programming and some preliminary layouts, so I understand what is happening behind the facade and what are those requirements for the facade for each of those spaces that we need to meet. So for example, in here we have a staircase and some transition and non-regular occupied spaces which are lounge, and I think there will be some coffee area and mostly just kind of this opening to the occupied roof. So for those spaces, we have a little bit more relaxed indoor thermal comfort condition because people can move around, they can adapt, they're not sitting there on their laptops next to the window and they cannot move. So those requirements are relaxed. We still want to reduce the cooling loads. We still will want to reduce the glare and some overlit, but we don't have to worry about it that much. There's also a lab portion of the building, and in general, labs are their energy performance is driven by the internal loads. All the equipment, the appliances, etc., and the envelope component in of their energy performance is not as big of a driver. However, we still recommend some shading and a lower window-to-wall ratio to prevent some, well, first losing the heat in winter and also prevent some overheating in peak cooling loads. But the main concern, not a concern, but the main goal for us was to optimize the major portion of the building, which is the regularly occupied open offices with some private offices and the conference rooms in a core that have exposure to south, north, east, and west orientations. And in here, because they have workstations assigned for the people, we really need to think about the daylight, we really need to think about the glare, we need to think about the internal thermal comfort. And because it's just such a big area and there's so much window area in there, we really have to reduce that total in peak cooling loads. So understanding what we're working with, but before jumping in the solar radiation studies itself, we looked into the sun angles, the altitudes and azimuths, the cutoff angles for the shading. The purpose of that was to, instead of start running shading options that architects wanted to give us, or maybe they had some sketches of that shading, we decided to give them guidelines that they can work with. So then they can use those guidelines through the filter of the architectural vision, create the high-performing shading device. So looking kind of separately from the south and east and west facades. For the south, as we know from our sun path, the sun dome, we mostly want to address the summer high sun, which, as we saw, have altitude of 71 degrees. So with that, we were looking into, if we were working with a window to wall floor to ceiling glass, we're looking at the 5.5 foot overhang just by using that 71 degree angle. That big of an overhang is not really realistic. It will create all sorts of problems, as all you know. First of all, it's expensive. Second, you will have structural problems, the snow loads, the bird nesting, all of the above. And no architects wants to see 5 feet overhang on their buildings, I'm sure. Our first recommendations to reduce that and to kind of avoid this problem is to provide a spandrel. Spandrels work great because, first of all, they have some insulation in them and they're already improving the thermal performance of the envelope itself. They also can help with overlit if they placed on the top or on the bottom, you know, depending on where and how they're located. You can modulate here. We usually, our first recommendation is start with 2.5 high spandrel because this is usually where the workstations are, but it's definitely up for, again, architectural vision. But if we have a spandrel and we have a few louvers, in this case 3, using that 71-degree angle, we can get away with only 2-foot louver, which is still quite a bit, but already better than 5. And then if we want to go even further, we can go with 0.5-foot louver, again with a spandrel and 4 of them. For east and west, as you can imagine, the sun is so low that if we wanted to work with the overhang, we will need all horizontal louvers. We would need a lot of them. It will be very, very dense shading device. So instead, we're looking at the azimuth of the sun or the horizontal cutoff angle. And in here, we would be using the 40-degree summer sun angle, which is the 3 p.m. for the west or approximately 9 a.m. to the east. They do. They are slightly different by a few degrees, but I think this one was for the west. And then doing the same thing, providing the guidelines for the architects so they can work with within certain ranges. So without any spandrel, without anything, our louvers, if we're doing 2 louvers with 3 feet span, they would be 2.5 foot deep, which can be, again, quite a bit, very expensive and kind of unnecessary, and also blocking a lot of views, which we want to have in this building. The next solution is, again, to add spandrel, improve the thermal performance of the envelope itself, and reduce that louver depth by almost 1 foot. And then the other one, the other recommendation here is to have the same dimensions, but tilt this louver a little bit. So we can have, it's the same kind of offset from the facade, but the louver itself can be 0.75 on 1 foot with the same span. So looking at all that, kind of providing those guidelines really for the architect, they come up with an interesting solution, we thought. So they combine the spandrel with the shading device itself. They also dropped the ceiling a little bit, which kind of which was required for the MEP, but also helped us to have a little bit smaller overhang. And then they stopped at 78 degrees cutoff angle, just for, again, structural, budgetary, and architectural visual purposes. But that itself helped to reduce the annual solar radiation by 19%, and the summer solar radiation almost, well, by 100 kilowatt hour per square meter, which is quite a bit. On the east and west, they again added this vertical spandrel, and they connected it to the shading device, and they worked with a 50-degree cutoff angle. That is even more than what we recommended based on our sun angles. However, in this case, we wanted to prevent the glare and we wanted to prevent the overlit. The project was going for the LEED daylight credit, which when this project started, there was no LEED 4.1, only LEED V4, and the ASE, if you're working on LEED projects, you may remember that annual sunlight exposure was quite a big problem. It was pretty hard to achieve that with floor to ceiling glass. So they kind of went even further than our recommendations. They went with this 50-degree cutoff angle, and they reduced this annual solar radiation on east and west facade by almost 60%. So using our solar radiation study from DIVA, we were able to get the monthly data of how much of that solar radiation is reduced every month, and then we kind of imported it into our energy model to see kind of way more precise how much those shading really help us to reduce the solar radiation. And then the north facade, solar radiation and reduce the energy demand of the building. And then the north facade really doesn't need any exterior solar radiation. It still have some diffuse solar radiation, and it may have the overlit, and it may have some glare because of the brightness of the sky. So for that facade, we strongly recommended the automated shades. Automated shades is something that really can save the energy for the building if you have the long-term exposure to that overlit or glare. So people who sit on the perimeter won't just draw the blinds down and keep them like that the whole day. They're more responsive to the outside. They open them when it's possible. They close them down when the when the conditions are acceptable. So that was our only recommendations for the north facade. Otherwise, there was no concern about the solar radiation. And with that, this is kind of what we end up with in terms of the shading on this project. So you can see that they really worked with the same element on the south facade and on the east and west facade. It's the same kind of the curved shading plus spandrel. I think east and west have a little bit more spandrel area, but they use them on vertical and horizontal. So they have this kind of unified look on a whole building. And it performs very, very well, as we saw in our energy model. However, not all the buildings need to have, or want to have, I should say, the unified solar radiation. And with that, I want to bring up another project, which was a little bit more multifaceted and a little bit more complex in terms of geometry. So this is a dormitory project on the northeast climate. In here, since it's a dormitory project, architects really did not have to worry how different windows look like from the inside, because you wouldn't see more than one window from the room or more than two windows from the room. So they really wanted to play around with the different solar heat gain coefficients of the windows itself and with the, solar heat gain coefficients of the glass, with the exterior shading and with frit. So they wanted to provide exactly what's needed for that exact window for the high performance, without it being kind of the unified, or without providing extra in areas when it's not needed. So the building is so multifaceted. The building is so complex, this geometry. This provides a lot of self-shading. Something that we would see on these two graphs in here. This is the summer incident solar radiation. Basically, you will see that it is also not as perfectly oriented to south and north. They had to work with the block, with the site that they were given. So we have quite a bit of area that is oriented to southwest and area that are oriented to southeast. There's also some interior, kind of a semi courtyard, I guess, areas in here, and then more of the self-shaded areas that are north facing. So the first thing that we did in here is to apply the solar heat gain coefficient of the glass to the solar radiation. We knew that they were going to go with the high performing glass, low E coating, very low solar heat gain coefficient. So that was our first step. And just looking on it, you can already see that our northeast and northwest facing facades are already performing quite well. They're already almost at the target, at the north, unshaded north target that we see. However, some of the southeast and southwest and some interior walls in there as well will need additional exterior shading. Since it's so complex in orientation, and since it's so multifaceted, and so there's so many different conditions, we did not look at the sun angles themselves. What we did is we looked at the solar radiation on the cylinder to see what is going to be the required cutoff angle of the shading for each of this orientation on the unshaded cylinder to achieve that unshaded north target. And basically by doing this parametric study, we came up with the cutoff angle for every single facet for the cylinder. The depth of recommended shading could have been reduced with low surging coefficient of the glazing, additional coats and frets, and this is something that we kind of recommended and architects did, and we'll take a look at it further. And when we combine this study with the previous solar radiation study that we did in here, we get those two diagrams, so which is the recommended cutoff angles on the southeast and southwest, which is basically combining how shaded is each of the cells, each of these testing points, and where is it oriented. So with that, we were able to understand which of the zones will need this very dense shading at 75 degrees cutoff angle, which of them are going to be between 80, 83, 85, and which of them at 90 degree cutoff angle, which is nothing, a flat facade. And you can see that the northeast wouldn't need any shading. The northwest will need a little bit of it. And then the southeast and southwest obviously will require some extreme, very dense or very deep exterior shading. The interesting point in here is this, is that in this case, in this project, they did not want to go with the, the curtain wall or with the floor to ceiling glass. It was more of the punch window scenario. So in here, the recess of the window is already acts like the shading. So we already had the 3 inches of basically the louver all over the glass. So our shading device itself can be 3 inches shorter. Now, similarly to the previous project, we didn't want to give design something for the architect. We want to give them all the design freedom. We want to give them guidelines or kind of the catalog of what they can work for. So we came up with this kind of 3 cases for 3 different sun cutoff angles cases. The first one would be the most dense one, 75 degrees. And in here, we'll look at the top row, which is high performance or heat gain of 0.3 glass with no fret. And in this case, we're looking at either 1.5 foot deep overhang or overhang with a vertical louver, or a few horizontal louvers at 0.8 foot. However, if we add the fret, which is going to go like a gradient from bottom to be the most covered area and kind of slowly becomes transparent to the top, so we kind of have the shading from the bottom by the fret and then shading from the overhang from the top, we can reduce it by almost a half to 0.8 feet. And then doing the same on other 2 options, just kind of reducing that required depth of the shading to 0.5 and another 0.5 with horizontal louvers. Then for 80 and 83 degrees, again, kind of doing the same thing, looking at the same typology of the overhangs, but looking at the vertical louver itself and then overhang fret, and we see a little bit less of the depth of the shading. And then for 83, which is when you just minor touch up, we're looking at the vertical louver of 0.5 or the fret itself. So that was kind of an interesting study because again, it's just so multifaceted and it's something that it's not as easy to resolve with the cutoff angles or with the azimuth and altitudes of the sun only. So the parametric studies, the grasshopper, and all the post-processing really helps in those cases. And then the last step that we did in here was to make it even more granular and look at each window itself, because basically we do not really care as much how much of the solar radiation falls on our opaque wall. It's not going to transfer heat. It's only the windows that we really care about. So the solar radiation and the massing also can tell you where you want to put your windows and where you don't, especially if you have certain, like maybe some high-rise or vegetation around your building. So with that, we basically just summarized for each window and which bracket of this cutoff angle each window is. And then architects, again, could play around with the catalog provided in here and apply it to every window and come up with this kind of the high-performing facade, which is very diverse. They wanted to have that kind of as you go around the building, you can see how is it different, how the shading is different. So it was definitely a very interesting study for us to work with. We really kind of nerded out on our scripts and post-processing. And with that, yeah, I think I have about 10-12 minutes left on the presenting for the solar radiation. I'm gonna ask again if there's any questions. And Junkie is probably muted.
Can you hear me?
Yes.
Okay, sorry, I was muted. We do have questions. The first question is from Paul Thompson. His question was, this analysis is very sophisticated. When did the architects realize that they needed help? And how do architects integrate preliminary analysis with massing studies?
Yeah. So I guess the facade studies are getting pretty granular and they're getting pretty sophisticated, right? The facade studies usually come to play when I would say definitely SD and early DD is time when we want to look at it further. We want to make sure that the estimates, the cost estimates, the structure is there for the shading. So how do they realize that we need consultants? That's a good question. Probably for architects, really. But as we're working, very rarely we have contracts with the architects just for the association study or just for the daylight. We usually can have the full scope environmental design contract with the architect. Bunny, I'm not sure if I'm breaking up again. Probably not.
Good now.
So with that, we can kind of tell you when your design is ready for us to take it to another step and get a little bit more granular. And we can kind of looking at the, again, direction that you're going with, kind of get a little bit more of a nudge in one or another direction. We can catch that maybe the massing that you're doing is, for example, let's just go back to this one. This is something that we got in a pre-concept phase as a massing. And we thought it was a great start because they already thought about the atrium, they already thought about some PV panels on top, they thought about the window to wall ratio. Our job in here was to optimize as much as we can of this design. And then when the architect decided to went another direction or slightly different massing direction, we were able to give them studies that supported that south-north dominant orientation. I'm not sure if it's answered the question, but basically I think that's usually why we are there to kind of tell you, let's try this. If we see, and if we incorporate in a design team, if we see how you design and what is the intent, what is the desire for the building to look like, we can catch those small things and tell, oh, this is actually a great idea because it can contribute here and here. And we're also going to be looking into it on it from so many different directions. We can tell you that this is going to contribute to your envelope thermal performance, but also can help with the daylight and also can help with the glare and come up with those synergies. So yeah, I guess it's not very direct answer, but I'm not sure if I have a better one.
Thanks, Ksenia. This is, oops.
We can hear you.
We're having all sorts of audio issues today. Go ahead, Paul.
Sorry about that. Yeah, I asked the question in thinking about this project right here. That was a major design change, and I'm sort of interested because I know I would, to make that change, I probably would have shown something to the client at that point, and then anyway, it seemed like it was a big deal to completely rethink the design of the building.
Right, and this is definitely something that was not completely radiation driven or completely, ATEX consultant driven. It was one of the maybe 7 design options that client discussed with the architect discussed with the client by the means of cost estimate, client recommendations, our energy models, our daylight models, radiation, and other consultant, MEP consultant recommendation. They decide to go with this. It's not always, and it's not almost ever that we can definitely tell, oh no, this doesn't work, you have to go with this one. And it's never really, very rarely, some design is a completely red flag and something that we cannot work with. It just so happened, I kind of wanted to show the realistic project that kind of worked out for us. It doesn't always work out like that. This one did. But no, it wasn't just because of us. It wasn't just because of radiation. It was mostly architecture and climate.
Yeah, sure. That makes sense. Yeah, thanks. It's a great presentation.
So Ksenia, this is Josh. I actually had a question. You were touching on solar heat gain coefficient and the role that can play. In general, I was curious if you had recommendations, based on different exposures and when it's really beneficial to push that and when it might not be, like do push it on an east or west versus a south, and maybe you can do something differently on the north and so forth.
Yeah, it's so in this project we were able to do that, exactly that. We were able to say you can go with a lower solar heat gain coefficient at northeast and northwest, while on the southeast and southwest you will have to go with a higher one or with a frit. And we were able to do that because it's a dormitory building and you're not going to see more than one window from the space from inside. But in a lot of cases, especially on the open offices or a lot of different projects, architects don't really want to see different windows, a different glazing in a one space. So for example, we have in this case this open office that goes all over, kind of from east to south, right? And it's just the human eye is going to notice that it's slightly different. It's the same kind of, we always have those conversations that maybe the TVs should be higher on the north, or maybe it should be lower on the east and west. And it's something that is noticeable, and it's something that is architects not usually going with kind of the different solar heat gain coefficient. The other thing, our recommendations are usually, again, if you have that high solar radiation exposure, we definitely would recommend that. You don't want to go too low. As you know, the passive house, for example, recommends quite high solar heat gain coefficients, so you can take advantage of the passive heat gains. And it's definitely depends on the climate that the project is located in. Something in the tropics or the west coast, those hot climates, Florida, all those areas. This is something that we definitely want to push for the very low solar heat gain coefficient. It is important in there. in this climate, in our climate, when we're looking at them, what are our energy drivers, the cooling is not always the one. There definitely are, and there's a lot of cases where it's a big driver. Again, because you have internal heat gains, you have some other factors that maybe are lower, so the cooling can be a driver. In that case, we would recommend to go lower. And in a lot of cases, we testing it in our energy model. We would see kind of around the whole building, or maybe the representative kind of block or floor. And just on a whole floor, let's say, the incremental reduction of the solar heating coefficient. And in a lot of cases on a northeast climate, you will see that savings, the energy savings at first are gonna increase, but at some point they will go down because you're not getting the benefit of the winter heat gains. So on that energy model, we're able to find that sweet spot. And then using that sweet spot, maybe it's going to be solar heating coefficient of 0.3 or 0.25. And then using that, we can find out what of that we can cover with the solar heating coefficient of the glass itself, and what of that will have to be covered by shading or frit or something else, because those strategies, those measures are also going to contribute to kind of the overall assembly solar heating coefficient, if that makes sense.
Great, thanks a lot.
Okay. Okay, any other questions? Great, let's move forward, and maybe there will be more at the end. Going to the solar energy, we're going to touch base on that today quite briefly. We didn't want to go too deep into, designing the PV arrays or designing the renewable energy systems, but we wanted to show how to use the solar radiation and kind of this analysis that's done in some positions to look at the potential of the PV panels, of the PV arrays early in the design on concept as the early DD phases, to understand, is it even worth it, to understand how, what is going to be the payback, etc., etc. So going back to our governmental office building in Boston, the one I've been talking the whole session. In the very beginning, this first concept that they have, we wanted to show that there is a potential for the renewable energy, so we can reduce that energy demand even further. So what we did is we ran in the concept phase, in pre-concept phase actually, we ran solar radiation on the PV panels with this just kind of one concept, which was I believe, yeah, west-east oriented, kind of this butterfly kind of scheme. And what we see in here, what you really want to understand is what roof area is feasible for it, what roof area is viable for it, and which is not. And in here, almost all of it is, because we don't really have any context over shading, we don't have any high rises, etc. But we do have those mechanical floors, those core areas that provide some shading on the roof. So we would probably recommend to remove those PV panels from here, because they're just not going to pay themselves fast enough to justify it. Same is happening right here. And then in going further in SD phase and DD phase, that is when we're looking into the actual layout of them. And we compared kind of the south-oriented PV array and again to west and east-oriented PV array, looked at what kind of tilt is going to be more efficient, more beneficial for the project, and how many of them we can actually fit. Because the trick in here is to design the span of the PV panels that are not going to cast a shading on one another. So the higher the tilt of the PV panel, the more spacing you have to have, because they're just going to cast a shade, and then half of your PV array is not going to generate any energy. So comparing the south oriented to west and east oriented PV panels, in this case, they were quite similar at the 5-degree tilt. You see more difference at the 20 and kind of the higher tilt between south and west. It's not crucial, but you still can see this difference. And then with the east and west, you can fit in a little bit more PV panels, but they can generate exactly the same energy as a little bit less PV area oriented to the south. But to talk about it kind of more generally, again, without getting into the specifics and to get more into, you know, how to think about it in the beginning, how to even understand, does it worth it? Is it not? Should we invest in, you know, something else that is going to be more beneficial to the project? But what I think is an interesting study to do, and something that we didn't cover in the previous sections today, is the shadow study. The shadow study is almost not an equivalent, but it's another way to look, I guess, under the overshadowing study. Just more kind of on a whole site or the whole building instead of a representative point. So in this case, what we did is we mapped all the shades of every hour of the day. I believe this was for the mid-season, to understand what area on the site was completely overshaded and you wouldn't have any direct solar radiation in here, and which area is only shaded for maybe an hour or two. This also was done on the project site without actually mapping the project. But in this case, we were looking at the possibility of PV canopy on site. We did have a few bike rack spots that we wanted to cover with the canopy. And in this case, this was a project on the campus. We wanted to have those PV arrays visible for the green education component. So that was a quite interesting thing to look at. So students would be able to see them right away. They, you know, it's a perfect place for them, but we really needed to see where can we put them so they would be generating energy. Another strategy that is quite popular, and every now and then we would get requests to study this option, is the building integrated PV. That was always interesting because there is just so much of the facade area that can be covered with the PVs, right, and to generate the energy. Again, it's go case to case. It's depending how much budget you have for it, where the building is located. Do you actually have enough exposure? As we've seen in here, we have a lot of benefit of having the 20-degree tilt or maybe 15-degree tilt, but when you go vertical, it's just not as effective. So it's I found it was hard to kind of justify it, you know, with a payback period. However, the technology evolves, and this technology is definitely coming. And the last project I wanted to share is this one. This is the Mill 19 campus in Pittsburgh. What they did in here is that they reused the old steel framework from the manufacturing that was there way back, and they designed the 3 core and shell projects under it. And they used this structure to put this gigantic PV array that powers all 3 buildings under it. And they didn't, well, basically they didn't close the that framework. So you can see the PV panels from the bottom when you walking around the buildings, when you standing on those balconies, when you're looking from the windows, you can see those PV panels from the bottom. The PV panel itself is translucent. It have about 7% light transmittance, so it's a good shading for those facades and for those windows. And at the same time, it still provides some light. It provides a diffuse light, and it creates that interesting, again, green building educational and element. There's a lot of screens, and there's a lot of kind of websites that lets you see how exactly energy they generate. It's a kind of very cool feature of the project. And yeah, they did not have an option to optimize this this tilt, obviously, or how they designed this PV array, but they picked a high efficient PV panel. I'll need to go back and check, but I think it was about 21% efficiency. Yeah, and it really covered quite a bit, if not all of the three buildings energy demand, at least of Coruscant. Yeah, and I think that wraps it up. I'm gonna stop. Well, actually, I'm gonna pause the share right now, and we can go over the questions for renewable energy or massing or anything else.
Yeah, Ksenia, you might want to just leave it up for the moment, but
Yeah.
I think that this last project is really fascinating to see the the use of solar as shading, and obviously the reuse of the structure. It's fantastic. Are there any questions from the group? Feel free to unmute yourselves. I know Janki's having fits with her audio, so she didn't feel that she should unmute or something might go wrong. But yeah, if anyone else has any questions about this, it was a really fantastic presentation.
Thank you.
Ksenia, I guess I'll ask one. In terms of the implementation of building integrated photovoltaics, what are you seeing in terms of the acceptance and the affordability, the accessibility of that technology?
Unfortunately, cannot talk to cost. Cost of it. It has been a while since one of my projects were interested in that, but we're definitely getting. I think architects are very interested and intrigued by it. I think it's an interesting facade element. However, on my project, it never reached, never passed through the SD.
Mm-hmm.
So we do have some studies. We're looking at the product. We trying to provide some research on that, but actually don't have any projects that actually implement that. So unfortunately, cannot providing first cost information or from a client. I think there's a lot of. I just don't think there is enough implemented. It's known enough yet, maybe, or tested enough yet for it to be as popular and as common as the PV arrays. Right,
and I think just as you're talking about the efficiency of these panels, I mean, I think that's ultimately going to be the driver for that, and
exactly. Yeah. Exactly, and another thing is the same thing for the efficiency is the solar shingles, and something that I'm getting asked very, very often, and just because especially on a smaller project, someone wants to see those kind of the big PV panels on the nice tilted roof, on a sloped roof. But again, it's a question of efficiency. The PV panels really it really improved. They're quite efficient now, and those kind of smaller PV shingles on the built integrated PV array are a little bit behind, at least from what I've seen. So it's definitely, when you're looking at a payback period, it is something that it's hard to justify. But hopefully, hopefully the new technology coming, hopefully the improvement coming, we're going to see more and more of them.
Yeah. Well, thanks again, Ksenia. It's been a great presentation. There's so much information here. I really appreciate it, and we're actually getting to the end of our time period here. So thank you again for running through all those examples, the different phases and different projects and different solutions. So I should probably go ahead and wrap up this session here.
Josh.
Yes.
Can you guys hear me? I was going to go over the tools.
Oh, go ahead. Okay, sorry.
Yeah.
If you're able to share, it's perfect.
Yeah, no, I just didn't want to mess up the audio for Ksenia if she was answering questions. So just if everyone can stick around for 2 more minutes, I was just going to go over some of the tools. I know Ksenia presented some larger projects, but we do have an audience who has smaller projects and might be wondering how they could use some of this analysis for their smaller or maybe residential projects or mid-sized firms that may not have the ability to hire someone like A10 to do some of this work for them. So there are tools that architects can use. This is a quick summary of the tools. And I'm not going to go over each item in terms of yeses or nos, but I do want to kind of just highlight some differences that are relevant. So for example, if you're using Insight in Revit, it does not take into consideration context, and the graphics might be more fixed if you're interested in presenting something in a very specific way. There are 2 free tools in here. I'm realizing I forgot to include a column that has a cost on there. So Insight is free with Revit. ComFen and NREL have a lot of resources. So ComFen is a tool by the Lawrence Berkeley National Laboratory, and then the solar resource maps are from NREL. And so you can use those to understand solar radiation in different parts of your project. So one of the good things about ComFen is you can actually do energy and daylight studies alongside with a solar radiation study on your facade and understand the trade-offs of different design decisions. And yeah, with that, I think the last thing we want to talk about is the solar radiation takeaways. So we had a lot of information. It was packed this session with a lot of examples. Try to summarize here for you. You kind of want to try to match your average solar radiation values that you see on your north facade along your other, your south, east, and west as much as possible to kind of minimize how much energy your building is using. Also, controlling solar radiation along the south facade is easier because the sun is at a higher altitude, making the angle of incidence on your facade shallower than 90 degrees. And it's harder on the east and west because you have the opposite condition. Your sun is lower and your angle of incidence is closer to 90 degrees. So a lot more of the solar radiation is being transmitted through your facade when you have the lower sun angles, okay? And lastly, all of the examples that Ksenia showed were really just showing you that you can use a solar radiation study at various phases of a project to allow you to select the material specifications and staging strategies. Sometimes before you're ready for an energy or daylight model, you can do it and then validate it afterwards with an energy or daylight model, because there are some rules of thumb that it allows you to implement without paying for a full energy model or daylight study. And that's it. Our next monthly meeting is going to be this Thursday. Please join us. There's a link right there. And we are looking for volunteers for our subcommittees. The 2030 commitment meets on Mondays, policy and advocacy on Tuesdays, environmental justice Wednesdays, and zero waste and design awards on the balance of the days. All right, well, thank you, everyone. I think that's the last slide. Yes, it is. And thank you for sticking around for a few more minutes.
Thank you. Great presentation.
Thank you all. Thanks, Ksenia.